My name is Bruce Keiser. I work for a company called Nalco, and we've been working in the area of air protection technologies in an attempt to help our customers, the power utility group industry, meet their Mercury limits. If you look at this first slide, I tried to show, or at least give you an example of where we are and where we're going. Because if you don't know where you are and you have no idea where you're going, you can't possibly get there. Unless, of course, you're a Harley driver who loves to just go out for the drive. And of course, we're generating power, so they wouldn't very much like that. So what I'm going to talk about today, or attempt to talk about, is give you basically a whole series of explanations on how to get to a reliable MATS compliance if your unit has a wet FGD for sulfur control. Now, I'm not going to read these slides to you. You're intelligent. You can read what's up on the presentation. So if you have any questions, okay, please stop me in the middle of the presentation. I'll be happy to answer those questions at that point. Now, I have to come back for a moment before I get into my presentation and ask in the audience, and yes, I've been put here before lunch to kind of keep you participating and awake. I've noticed a lot of empty coffee cups at this point. I assure you, I went and talked to the cafeteria. They don't stop serving until 2:30. Believe me, I will not keep you until 2:30, okay? But the question I have for you right now is, how many of us fly? Just a show of hands. How many of you fly? That's great. That's great. How many of you are pilots? Okay, so about 2 of you, okay? There's really a difference between flying and being a pilot. If you look at typically your Chicago O'Hare, which I've been through quite a bit recently, you see a lot of people that fly, okay? If we look at flying historically, okay, in the beginning, we were flying basically open cockpit planes, exposed to the environment, but more importantly, how did we know we were getting where we were going? Well, they basically had a compass, and they had a little watch, and you know why the watch was there? To calculate how much fuel they had left. Of course, you want to have enough fuel to get where you're going, right, when you're flying? Today's planes, okay, are much more advanced. They fly through all kinds of weather and get to very exotic places that we want to go to. And as a consequence, the instrumentation that is found in the cockpit of that plane that you are getting into is much more advanced. And a lot of things that the pilot and the co-pilot have to look at as they're flying. As you sit there with your iPod open or your newspaper, or in my case, you simply fall asleep, with the assurance that when you wake up or when you're done reading that paper, you're at the destination where you wanted to go to in the first place, why you got on the airplane. And you're going to wonder, where am I going with this? Hopefully you'll be able to see that by the end of this presentation. So here are the 5 different things that I'm going to go through today that are going to get you to a reliable Mercury capture along with a wet FGD. These are the things that the utilities are looking at right now to make sure that they are MATS compliant. Let's talk about flue gas measurement for a moment. Connie has already talked about this a little bit, but I want to re-emphasize this. This is probably the most overlooked aspect of any demonstration or any set of data that is presented in any conference anywhere where you attend. Many times we will say, and when we run a demonstration, we will insist that you have multiple means of making a measurement, of monitoring that mercury. And many times people will get up and say, hey, I've got great correlation between 2 methods. I'm showing you here on the left and on the right. On the left is elemental mercury, and Connie has introduced that earlier. This is a great correlation, 0.97. So if somebody gets up and says, hey, we got great correlation, we're okay. Unfortunately, this is where where you want to be, where the SIMS, okay, where the continuous measurement is equal to the measurement by carbon traps. If you're over here, you have a great correlation, but what is that telling you? It's telling you your SIMS is not beginning to, or the data that you're reporting is not beginning to be giving you the accurate measurements. This is a classic problem. If you don't know what's going on around your mercury measurement, you don't know where you're going. If you don't know the total, which is the easiest to measure at this particular point, which is at the stack, there's no way for you to get any kind of information on your elemental composition at the stack. And that becomes a critical problem. If you see this kind of data, you have to ask, what is going on? You have to raise a red flag and say, let's take a step back. We really can't go any further on this. This is some data that was collected over a series of demonstrations to show you where you really should be looking, okay? And here you can see that we actually match up on the line, and so that your carbon traps match your SIMS, and the data you can begin to understand. Yes, you're going to see outliers in that data, but then you have an opportunity to begin to understand why that's an outlier and help the industry and help the SIMS people actually figure out what's going on. You definitely want to get high correlation coefficients and on a good agreement between multiple measurement techniques. That's the first step. And as I've been saying, if you don't know the heading, which is the mercury measurement itself, you have no earthly idea where you're going. The second is you have to manage the flue gas speciation. And Connie has already talked about this, talked about the fact that the oxidation fraction depends on the chloride and the bromide concentration, and it is impacted by all the other things in the flue gas. This is, again, kind of a repeat in the sense that there are three things that you do to control your oxidation state. You can do a fuel mix. A lot of the utilities are doing some fuel mixing, which means that they're bringing in chlorides from a different fuel source to increase their oxidation. That's a very difficult thing to do because it requires more space, more land, and management of very large quantities of fuel. The second is a fixed asset like an SCR, and we've talked about the benefits of that. One of the things that you need to keep in mind is two things. With an SCR, the relative age of that SCR is going to degrade the amount of oxidation of mercury you're going to get, which means it's going to become more and more difficult for you to meet your MATS compliance over time. The second thing you have to keep in mind is if you don't have good exposure of the flue gas to that catalyst, you're not going to get the full extent of your oxidation. So now soot blowing, the buildup of particulate on that catalyst becomes a significant thing. And if the plant is not continuously looking at that or monitoring that, you will get degradation in your oxidation. And then finally, as Connie has talked about, there are boiler additives and fuel gas additives that will actually help you increase that oxidation. And they can be used in any kind of combination. The point of the matter of those few slides is this establishes your altitude. In other words, this establishes how good you can get with the equipment that you have on site already. Okay? If you can't get to your oxidation state of mercury, get that below your MATS compliance limit, you have no chance of meeting MATS to begin with. This is a simple example, and one of the things, quite frankly, that in my industry, and I do the same thing, I complain a little bit about is we talk an awful lot about percent oxidation, percent speciation, and I mean, honestly, you all probably have done the math several times, but you have to be aware. 80% oxidation for a given, across the board does not guarantee what the elemental concentration is going to be. 80%, and the point that I'm trying to make, quite frankly, is if you look at that, 80% of 34 pounds per trillion is a lot different from 80% of 8.33% pounds per trillion. So percentage is great, but at the end of the day, it's really how much elemental mercury is in your flue gas. And that's what you want to manage. Because at the end of the day, a wet FGD captures ionic, and you really want to get this number down to below the 1.2 pounds per trillion. That's where you're trying to get to. I'm going fast. I haven't lost anybody yet. You still all there? I haven't seen too many iPods come out, so I guess we're still okay in terms of flight. So I'm still entertaining you, keeping you here. So you have to once you've got the speciation that you've managed, and quite frankly, you can do that in several different ways. You can provide, as I indicated, you can get to that point in many different ways. But then you have to master mercury within your wet scrubber. And quite frankly, I've taken a very basic approach to this. I've drawn, no, not a black box, I apologize, but it's actually a red box around the wet FGD and schematically presented it here. And basically, and excuse me, I'm going to move just a little bit. Basically, what you're seeing here is this is your flue gas coming into this box. You have a lot of things going on. You have two things coming in. You have your flue gas. You have reclaimed water, which is absolutely what you want to do. Your reclaimed water is coming into your scrubber. And you have two things coming out, typically. Your scrubbed gas and your blow down to either gypsum production or wastewater production. And quite frankly, you have to. The utility has to manage all of these things in order to manage the stack number. That's the point. If you have no other memory of this presentation, that's the thing that you have to remember. Because in the scrubber, just like in the flue gas, there are many different forms or places where mercury hides. It hides in the flue gas. It comes in as elemental and ionic. It hides in the water. The ionic can be absorbed very effectively. The point is very soluble ionic mercury, very insoluble elemental. Elemental will typically go through the scrubber, okay, because of the low solubility in the water phase. You will also have mercury captured within the scrubber itself in the solids as well as in the water. When these solids are removed with the water to wastewater, they will, in fact, they can come back in as soluble mercury back into the scrubber. And so it initially acts as a capacitor, if you will, okay? And you have because it's a capacitor, initially, you have a high loading of mercury, which means you can exceed, in the stack measurement, more mercury than you actually are bringing in your flue gas. But that's another story, and I don't want to get into that at this point. The point of the matter is you have to be aware of these different forms of mercury. You do, in fact, manage them, and you manage them in many different ways. We're talking here about a phenomenon called mercury reemission, and what happens within that scrubber, within the water phase and the solid phase of the scrubber, is you actually see the elemental mercury increase from the inlet of the flue gas, from the flue gas inlet to the stack itself. And where does that elemental mercury come from? This is meant to be a cartoon. This is a cartoon of analysis, okay, SIMS data. And what you actually end up seeing here is this is your MATS limit right here, okay? And if you look closely, this is your elemental mercury coming in at about 0.3 or at 3 pounds per trillion. And this is your elemental mercury at the stack. It's higher. And that difference, is what we call reemission in the industry. Okay? There was a graph put together, actually this was put together by B&W. Not stolen, I have some permission. There's the reference. But the point of the matter here is all summarized in this last line. If your reemission goes up, okay, your stack emissions are going up. So if you don't control this, okay, it does not matter how good your oxidation is. It does not matter, okay, what your emission limit is, because if you don't manage this, you will not be in compliance. The key here is the difference between control and compliance. In some units, we've seen scrubbers, and Connie's data clearly shows this from the 1990 ICR data. You have some scrubbers that are compliant and some that are not, and that relates to where they are on this line. In other words, how much re-emission they have or they don't have. In some cases, you don't have to control the re-emission, and you can still be compliant. This tends to be your tach. If you fly, this is your tachometer and your engine temperature. This is what drives the whole thing. If you don't keep an eye on this, you're not going to be able to keep that airplane in the sky. So it is about a reliable strategy that goes across the whole plant. You have to control the speciation, you have to control the scrubber and what's going on within the scrubber, and you want to look at what's going on around the plant effluent. Okay, so there are three things that you can do around your scrubber. Consistent, you have to get your wet scrubber to become consistent. Like everything else, it works. They're generating power. The power utility is about making sure your lights are on at the end of the day. You can have your heat in the middle of winter. Scrubbers are there. They take care of SO2. That's their primary function. They haven't been required to look at mercury removal or co-benefit. It's time now to put another instrument on their instrument panel to pay more attention to that so that they can consistently meet the MATS requirement. The second thing they can do is use wet FGD additives to actually help that control, to have a strategy, a lever, proactively to control mercury within the scrubber. And then finally, best of all, you want to automate that so that it's constantly being monitored and it's not through all of the swings, including, as we heard this morning, talks about startups and shutdowns, and it will actually respond to those kinds of changes in load automatically. So let's talk about some of the consistent wet FGD operations. This is taken from the literature. This is well known. If you're looking at data from a submission, you may not see all of this information, but these are some things that are important. I'm not going to read all of them. Sulfite, liquor pH, and ORP are things that can be monitored within the scrubber that gives you some idea of what's going on. I can tell you right now that from my perspective, these are great. These are general, consistent operational parameters, but they are not levers that you are going to pull or knobs that you are going to turn as an operator to get your unit into compliance immediately to avoid it from going out of compliance. Okay? And there are benefits and there are disadvantages to each one of these strategies. And actually, quite frankly, you want to combine these strategies, optimize it, to get to the point at which you've minimized the amount of re-emission that you might be seeing. Scrubber additives, there are a whole host of them, starting from carbon, which can be added either up front of the scrubber or into the scrubber, to a whole slew of various chemistries, and there are more coming on the market daily. Each of these has their advantage and disadvantage. The key here is re-emission and mercury control starts with controlling mercury. And each of these binds mercury and prevents it from participating in the reductive reaction that generates elemental mercury. So simply put, all of these function one way or the other to complex mercury and remove it from the wet scrubber. This is your oil pressure if you're a pilot. This makes sure that your engine is constantly lubricated and has the potential to continue to function the way you want it to function. And finally, automation and control. Automation control is absolutely critical because now this unit not only captures sulfur, but it's also going to be required to help you capture. Yeah, I'm a Harley driver. What can I say? It also is now capturing mercury. And so as a consequence, you want to constantly look at the unit operation and how it's affecting the successful capture of mercury. So you're looking at the chemistry which is going on, the unit operation around the wet FGD, as well as the unit operation around the boiler. Because as we've heard already this morning, boiler operation also impacts mercury coming through this system. You have a feedback system to a smart controller with an algorithm and sensors that has the process inputs, the chemistry inputs, and then controls your scrubber additive and basically is tied into controlling your match compliance. This automates the system. It allows you to control through shutdowns and startups and swings in load and responding to the demands put on the unit. So, all in all, this is about all 4 steps, 5 steps, measurement through strategy application. And I want to just give you a real quick, this is a unit that we ran a demonstration on that has been worked on. Air heater, the key here is it's got an SCR on it to give you oxidation, fabric filter, wet FGD. You can also look, you have the notes, so I don't have to go through. You can look at the sulfur content. This is a bituminous coal unit. This is the data of the first 50 days of data that was collected from their SIMs. The green dots are actual soluble mercury measurements taken from the wet scrubber. And you can actually see here, unlike some cases, I want to emphasize here, this is only an issue if you are looking at or you happen to get data at this particular point in the test. If you come to these, early on in the industry, we had a problem where people did not believe that there was reemission. And the reason was the reason being that they would go to a unit and there would be no reemission. Why? Because we were making measurements at these points. Units like the wet FGD will in fact, and frankly it doesn't really matter what is up front of that wet FGD, it collects mercury. And over time, if you don't manage and control the mercury, you end up having these spikes in emissions, which end up being issues with respect to compliance. The key here, the other thing to look here is does appear to be a correlation between the soluble mercury content, which is in logarithm scale, versus the emission itself. People said that they couldn't see that quite well. I've looked at enough of this, so I thought I'd break this out real quickly. This is the first time that anyone has seen this data in the industry, as far as I'm concerned, as far as I know. So here, this is real live data collected from a demonstration, and you can see that there's a grouping down here, of course, because this is during the demonstration itself, and this is baseline data. And I have a very good correlation, about 0.88, 0.9, 0.88 correlation between this data. And the statisticians in this room would say, well, yeah, because there's a big group up here and a big group down here, so there's got to be a line through those. And that's probably true. That is true. But in point of fact, if you look down here, there's also scatter in this data, as you can see, and the question becomes, what's causing that scatter? If you can explain the scatter in this data, you can begin to understand where all of this is coming from, how to control these units. And I contend that there is a way. Here is the model that would fit to this data. And we can only fit this, that you can only begin to do this work if your measurement is good. If your measurement is crap, excuse the expression, then you cannot get this kind of data. This is real life, unit operation, day-to-day, variable load data, and you can see that the correlation coefficient here is 0.995. That's pretty doggone good, and you can see that the variation down in here has pretty much disappeared across here. And what has happened? As I told you earlier, you've got to have a good measurement. What was the second thing I told you you needed to do? Control your speciation. If you don't control your speciation, you're at a disadvantage to begin with. When you start adding in the elemental content at the stack, that tells you about your oxidation coming into the wet FGD, and that's what happens. So we're beginning to build models. Models lead to automated operation that allow you to be reliant and compliant across with regulations. And in point of fact, here's 60 days elapsed time that shows that we have been compliant over the 60 days. And in point of fact, this unit has been compliant to their goals and their regulations for over 15 months now. So, decrease your stack emissions. Here's your summaries. Reliable mercury compliance achieved through managing your oxidation, managing your reliable measurements, and in point of fact, making applications and controlling your mercury within the scrubber. We can talk about absorption, we can talk about re-emission. At the end of the day, it's about the stack measurement. It's about being proactive on running these units. So that when the operator comes in on the day, he can casually walk up the ramp to his control room. You know, we can comfortably, as users of electricity, get on the plane, pull out our iPods, pull out our papers, and comfortably relax, knowing that we'll get to where we want to be. Because we have the right instrumentation, we have the right information, we know where we are, and we know where we're going. With that, if you have any questions, I know I've gone fast and I've gone over just a little bit. I apologize. Any questions? Yes.
Why weren't there any data in the middle of those two plots? You had highs.
Excellent question. Excellent question. Because we collected data and then we applied the solution. Okay? And the solution, the application of the solution is quick enough that you don't get a lot of transitional data. That's a great question. And actually, you don't want us to run a unit somewhere in between those. We have to get to compliance, right? Yes. So the question is, would it be simpler to reduce the amount of water being recirculated back into a scrubber? There's a lot of different ways to look at that question, frankly. Obviously, if we recycle water, that's a good thing. Because the more water you consume, the worse it is for the environment, and we don't want to do that. So recirculating water is absolutely critical, I think. But there are some units that would run once through or low recycle rates. And in those cases, yes, it gives them a benefit. They can run perhaps a little bit better, okay, without the potential for re-emission. But again, it has to do with the simplest answer to your question is, and I really want you to go away with this answer more than anything else. There is not one solution that fits every unit that it is either out there or will be built, okay? And as a consequence, whether or not lowering the recycle or the reclaim rate of water on a particular unit has to do with how good their back end is, their wastewater treatment plant is, what they're doing with their solids that they're generating, and also the overall size of the unit itself and the water that you're talking about. I guess that's the simplest answer. But yes, I mean, initially that makes sense, and you can certainly do that. Yes, yes. I don't think we would want them to do that in the long run. The best thing to do, I mean, honestly, the best thing to do is to get the mercury out of the water, out of the air, out of the water, into a controlled system where we want it to go. And that's what we're proposing. Put it where you want it to go. Long. I know you're hungry, okay? Okay, so wake up, put your iPads away, go to lunch. Exit to the far right.